When you flip a light switch, what actually travels through the wire? Electricity, electrons, or something far stranger? Most people imagine electricity flowing like water inside a pipe. It feels obvious. It feels correct. But it is completely wrong. Electrons inside a copper wire move incredibly slowly, slower than an ant crawling across a table. Yet when you flip a switch, the light turns on almost instantly. How is that possible? If electrons move slowly, energy must be traveling in a completely different way. Richard Feynman revealed the shocking truth. Energy does not flow inside the wire. It flows around it. The wire is not a pipe carrying energy. It is a guide shaping something invisible. The moment a circuit closes, an electric field forms instantly around the wire. At the same time, a magnetic field wraps around the conductor like invisible rings. Together, these fields carry energy through the space surrounding the wire, straight into the bulb. This idea feels uncomfortable because it destroys the simple story we learned in school. We were told electrons carry energy like trucks carrying goods on a highway. But in reality, the electrons barely move forward. They only drift slightly. So if electrons are not racing through the wire, what is moving so fast? The answer is the electromagnetic field, and it moves at nearly the speed of light. Energy flows in the space between the wires, not inside the metal itself. The copper does not carry the energy. It guides the field. Think of the wire as rails. The train is the electromagnetic field. When the switch closes, the field reorganizes instantly across the entire circuit. That is why the bulb lights up immediately, even though the electrons barely move. Physicists describe this energy flow using something called the Poynting vector. It shows the exact direction in which electromagnetic energy moves through space. And when scientists calculate it, they find something shocking. The energy is flowing in the space around the wire, straight into the device, not through the center of the copper. So what are the electrons actually doing? They are responding to the electric field, pushing slightly against neighboring charges, like a line of billiard balls touching each other. Push one, and the motion transfers instantly. The balls barely travel far, but the effect moves extremely fast. Electric circuits behave in a similar way. Local motion, global response. But if energy flows outside the wire, then why do wires heat up? Why does too much current melt metal and cause sparks? The answer lies in resistance. Inside the wire, electrons constantly collide with vibrating atoms. These collisions convert organized energy into random motion. And random motion is what we experience as heat. So the field delivers energy to the wire, and resistance turns it into heat. In a light bulb, that heat becomes light. In a heater, it becomes warmth. In a motor, it becomes motion. Now think about this on a larger scale. Power plants are miles away from your home. Yet when you flip a switch, your room lights up instantly. The energy did not travel all that distance in that moment. The energy was already present in the electromagnetic field around the wires. The generator simply maintains and reshapes that field continuously. Electricity is not a substance. It is a relationship between fields and matter. Wires guide it. Devices transform it. But the real action happens in space itself. Once you see this, the simple water pipe picture falls apart forever. Electricity is not just moving particles. It is dynamic, invisible geometry shaping reality. And the next time you flip a switch, remember, the energy lighting your room is flowing through space around the wire, not inside it.